In late 2018, thousands of office printers suddenly woke up and spit out a bizarre demand: subscribe to a YouTube channel. Attackers hadn't walked into these offices. They had exploited an open network port and uploaded a custom script disguised as a firmware update directly into the printer's memory. It sounds like a harmless prank, but that exact same vulnerability profile, overriding a device's core logic from the outside, is what attackers used in 2015 when they infiltrated Ukraine's utility grid and cut the power to 700,000 people. We usually think of computers as the laptops and servers we interact with daily, but a printer or a power substation controller relies on an embedded system. This is a stripped-down, purpose-built computer engine designed to do one specific job over and over again, entirely hidden from the user. To save time, software engineers often recycle code from standard desktop operating systems, like Windows or Linux, and funnel it into these tiny hardware constraints. Recycled code brings decades of desktop vulnerabilities into the embedded device. The paradox: you can reboot a laptop for a patch, but an embedded hospital ventilator or telecom switch cannot go offline. Security updates bounce off strict uptime requirements, leaving devices completely exposed. Look closely at our city streets and office buildings, and you'll realize we are surrounded by millions of untracked computers. Cash machines, smart thermostats, and security cameras all rely on these hidden operating systems to function. In the past, devices used highly trimmed-down systems like Windows CE, which kept functions strictly isolated. Today, manufacturers prefer systems like Windows 10 IoT. It gives developers full access to the standard Windows API, making it incredibly easy to connect devices together and push new features. By running robust, interconnected software on cheap commodity hardware, every coffee maker or smart bulb becomes a fully capable doorway into your wider network. This image shows a firmware update tool for an office multifunction printer. Because these devices perform multiple jobs and are rarely scanned by IT departments, attackers can package malware to look like a legitimate update file, slipping right past firewalls. This massive attack surface expands even further when you add our personal hardware to the mix. Bluetooth wearables and Trojan applications hiding inside official mobile stores provide attackers with direct bridges from our pockets straight into the corporate network. At the consumer edge, the market demands that devices talk to each other flawlessly right out of the box. Interoperability overrides strict security, creating a sprawling, highly connected landscape that rarely sees a software update. Defense, aerospace, and critical infrastructure operate on a timeline of pure survival. In these environments, embedded software dictates physical outcomes in real time, where a single microsecond of latency triggers a catastrophic failure. These environments require a real-time operating system, or RTOS. Instead of juggling tasks whenever it has free memory, an RTOS executes commands in a mathematically predictable sequence. This exact architecture, specifically the VxWorks OS, is what NASA relies on to drive rovers safely across the surface of Mars. This chart shows how these systems are structured. On the left, a monolithic kernel runs core processes in shared memory. A breach compromises everything. On the right, microkernel architectures strictly isolate services. If one application is hijacked, the rest stays intact. This segmented approach is why commercial RTOS software, like QNX, runs inside the ultra-high availability Cisco routers that form the backbone of the global internet. The engineering choices made on day one are permanent. Whether you use a monolithic or microkernel design determines whether a single line of bad code simply reboots a background service or sends $1 billion space probe hurtling helplessly out into the dark void. Even the most robust architecture has a blind spot. The ultimate threat to any embedded system is a firmware rootkit, a piece of malicious code designed to burrow past the operating system entirely and infect the device's deepest physical memory. These infections are remarkably small, allowing them to hide quietly in low-level, non-volatile storage areas, like the flash memory or the system BIOS. Design flaws in laptop theft recovery services have shown exactly how attackers exploit these low-level layers. Because the code lives on the chip itself, standard antivirus scams can't see it. You can wipe the hard drive and reinstall the OS, and the rootkit will simply reinstall itself the moment the machine powers on. By hijacking the hardware before the software even wakes up, attackers render high-level security protocols completely useless. Because we can't reliably push software patches to these edge devices, defense has to start at the physical level. Security teams employ trusted platform modules, dedicated chips that use cryptographic keys to physically verify the firmware hasn't been tampered with before the system is allowed to boot. Once the hardware is verified, the next step is absolute network isolation. Administrators must map every single embedded device in the building and strictly sever the connections between non-essential hardware, like the lobby printer, and critical network controllers. Finally, administrators shrink the attack surface by enforcing data transport encryption, applying the principle of least privilege, and aggressively turning off any network service the device doesn't absolutely need to perform its core job. Millions of forgotten, invisible computers now form the actual foundation of our global infrastructure. Securing them requires moving past high-level software and verifying the hardware itself, ensuring the hidden engines we rely on can't be turned against us from the inside out.